Hi, my name's Michael de Podesta, and this is a short talk about my attempt to become a carbonaut, someone who lives their life without emitting carbon dioxide. So let's begin. So here's the stupid logo, and I gave this talk to Richmond U3A in September 2021. And now I'm going to try and recreate the buzz of that original presentation. So let's begin with the PowerPoint. So there are sort of four parts to the talk, and the first is about the climate crisis that we're in. Then there's the question of how much carbon dioxide I emit, and then there's what I've done so far, what it all cost, and then we'll just look at where we're all up to. So let's just begin by looking at the climate crisis. I won't say much about it. You all know about it. It's in the news all the time. The Earth's average temperature is increasing. The temperature of the atmosphere is increasing. The temperature of the land is increasing. The temperature of the oceans is increasing. The temperature of the deep oceans is increasing. The sea ice is melting more on a progressively each year. The whole planet is just warming up, and we know why it is. It was predicted before it happened, and it's due to carbon dioxide in the atmosphere. Now, there are other contributing factors, but by far carbon dioxide is the most pernicious element and the dominating element in the warming that we're experiencing. So here's just what carbon dioxide is like in the atmosphere. If you can imagine the molecules of the atmosphere, if you could pick 100 of them, you wouldn't actually see any carbon dioxide molecules. You'd see nitrogen mainly, a little bit of oxygen, and maybe one argon atom. And if you looked at 1200 atoms, you'd begin to see a few water molecules as well, but still on average you wouldn't see a carbon dioxide molecule. But if you looked at 10,000 molecules, now you can begin to see some carbon dioxide molecules. On this picture of 10,000 molecules you should see 4. Just in case you can't quite spot them, here they are. Can you see them now? Let me just make them bigger and wave them around a little bit just so you can spot them. There we go. Now this concentration in the atmosphere is that's 4 carbon dioxide molecules in 10,000 air molecules, which is 40 carbon dioxide molecules in 100,000 air molecules, or there'd be 400 carbon dioxide molecules in 1 million air molecules. So this concentration is called 400 parts per million, or 400 ppm, and that's the common way people refer to the amount of carbon dioxide in the atmosphere. And there's it's really culturally important measurement of carbon dioxide that's been it's been measured continuously since 1959 at the Mauna Loa observatory in Hawaii. You can see on this picture that Hawaii is very geographically isolated. It's a long way from any of the sources of carbon dioxide in the industrial world, and so this measurement gives us an interesting average of emissions from all around the world. And here's the graph. It's called the Keeling curve after the scientists who began it, and you can see it runs from 1959 up to the present day, and you can see it's increasing. That's the problem. It goes from we estimate before we started emitting carbon dioxide in a serious way, there was about 280 parts per million, and now there's just over 400 parts per million. Now, I want to show this graph to you. It's the same data, but I want to change the left-hand axis. So here it is. So now, instead of putting the concentration of carbon dioxide, I'm plotting the mass of carbon dioxide in the atmosphere. And you can see the unit is a very big unit. It's measured in gigatons, 1 billion tons. And what we see is that historically, just click twice there. Historically, there was around 2,000 gigatons of carbon dioxide in the atmosphere. 2,000 billion tons of carbon dioxide in the atmosphere, and the effect of the carbon dioxide we've put in there is to increase that to just about 3,000. It's a little bit below 3,000, but that's a good round number to discuss. And it's currently increasing at about 18 billion tons per year. So how does it get into the atmosphere? Well, historically, this is the way carbon dioxide moved around. Now, all the numbers in this are all in billions of tons of CO2, so they're enormous numbers, and you don't have to try to get your head around it. Just look at the relative magnitude of them. And so they're a big reservoir of carbon dioxide in the atmosphere, in the top layers of the ocean, the ones that exchange and mix with the atmosphere regularly, and in the deep ocean, the ones that exchange carbon dioxide with the atmosphere much more slowly. We've got the growing things on Earth, the leaves and plants and so on, and the soil. Every year, every day, all the time, there's a constant exchange between all these different sinks of carbon dioxide. So plants grow and pull carbon dioxide out of the atmosphere, and then they decay and out it comes again. In the same way as the temperature of the ocean changes, carbon dioxide is emitted or absorbed. Every time there's a wave, there's little bubbles, and air is held next to water, and carbon dioxide can move between the water and the air. All these processes go on, and you can see there are hundreds of billions of tons exchanged every year. So these are dynamic processes that keep all these numbers roughly stable until humans came around. So now at the beginning of the 21st century, we've got a legacy now for 100 or 200 years of accessing the amount of carbon in the earth, so historically deposited from plants and so on, and we're getting access to that for all the benefits we get from it, and emitting 36, again it's round numbers, 36 billion tons of carbon dioxide every year. So the first thing to notice is just that 36 is much smaller than all those other numbers. So that's why this is not completely overwhelming everything, why it's happening slowly. And so 36 currently is about 9 billion of those tons is absorbed in extra plant growth. About 9 billion is dissolved in the surface layers of the ocean, and that's a quarter each, and roughly a half is going into the atmosphere. So currently we have about 3,000 billion tons in the atmosphere, and it's increasing at about 18 billion tons per year. And these processes of dissolving it in the oceans and growing extra plant matter can't get rid of it. It's going to stay in the atmosphere until it's either dissolved or taken out in some other way. So here's the situation now. We're going from 2,000 billion tons up to 3,000 billion tons, increasing at 18 billion tons per year. And what's the effect of this? Well, it affects the way infrared light moves through the atmosphere. Now, there's not enough time to go into this, so this is just a snapshot of how it works. That we know that the Earth is warmed by the sun, and if you average the power of the sun over night and day and all the land area of the Earth, you'd get an average of about 240 watts per square meter warming the Earth. That's really quite a lot. That's why the Earth is so nice and welcoming to human beings. But if you just had that warming, the Earth would just get hotter and hotter and hotter. So we have to radiate energy out into space. And so roughly speaking, we radiate 240 watts out into space. But the Earth is warm enough. The Earth is warm, and it radiates more than that from its surface. Now the atmosphere isn't transparent, and so what happens in the infrared, so the atmosphere is pretty transparent in the visible, so sunlight just comes straight through. But as the Earth's surface tries to radiate infrared light, the atmosphere at those wavelengths looks misty, and so, like foggy, and so the radiation from the surface of the Earth gets scattered back to the Earth. It's a bit like headlights in a car when you're traveling in fog, and so this infrared light gets scattered back down to Earth. And Guy Callender, one of the first scientists, in fact the first scientist to discover that the Earth was warming from this effect, called it sky radiation. And I like that. It's radiation coming from the sky, whether the sun's shining or not. And what we've done is we've added extra carbon dioxide, and that's made extra sky radiation. And that 150 watts per square meter that we had originally has become about 152 watts per square meter. And amazingly, that small difference is just over 1%. That's what's warming the Earth and delivering us these difficult problems. So who's to blame for this CO2? Well, you're staring at the climate criminal himself now. It's me. I'm responsible. Take me, officer. Well, it's me. It's not just me, because I can't emit billions of tons, but it's me and people like me. So in the UK, most people emit a few tons of carbon dioxide every year. Now, just want you to get that round your head. A few tons of carbon dioxide. Now, probably, I don't know what your household is like, but probably you do not put 1 ton of garbage outside your house in a year, and yet you emit a few tons of carbon dioxide, and you probably have no personal consciousness of having had a few tons of it and then getting rid of it. So that's why it's important to understand how these carbon dioxide emissions occur and what you can do about them. So I'm just going to pause at this point, and we're going to change the video file. But we're back here now. We've just finished part 1.